Good morning, everybody. My name is Sven Niese from the company of AXO Dresden. We are doing mainly multi-layer X-ray optics. This talk here will be a bit more of an overview of different micro and nano-focusing X-ray optics mainly for hard X-rays. And then at the end, I will talk a little bit more in detail about the Multilayer Laue Lenses, what was part of my PhD thesis now 10 years ago, and I'm still working on together with the colleagues from the Fraunhofer IWS. And the entire talk will be at least a bit from an engineering perspective, since we are actually manufacturing those optics. We want to apply them to the instruments and so on. So in the end, it all needs to work somehow, and one also wants to put a sample in at the end. So this direction. Okay, good. There is this site xrayoptics.de from, I guess it's from Arndt Last. And this kind of overview is a bit inspired from him. So there are different types of X-ray optics. Reflecting ones, that's the one where we are mainly manufacturing. Diffracting X-ray optics, where you find the Multilayer Laue Lenses. Refracting optics, and also quite simple, some optics that are absorbing or phase shifting and so on do also belong here. Except for this, one has to consider the photon energy that you want to work with. If you want to do some beam shaping in 1 or 2 dimensions, of course efficiency is always interesting, and then also the effort to manufacture those optics. So some equations here. For the crystal optics, for the multilayer optics, you kind of have a lattice what diffracts. And in order to get the angle, you have the Bragg equation. The graph here shows the situation for a nickel-carbon multilayer. What's kind of a typical multilayer that we apply. For the multilayers, the period, so the d, is larger than for the crystals. Therefore, all the angles are smaller, and you can see that you will have the first order Bragg peak here in the order of a bit more than a degree. If you go to higher energies, the wavelengths gets shorter, and therefore also the angles get smaller. This means if you look for the same multilayer at, for example, 25 kV, all the angles shift to the left. What has to be considered, of course. The decrement of the index of refraction, this mostly goes with e to the power of -2, so with the photon energy. Means also that all the optics that kind of depend on this effect, this is all reduced with the increasing photon energy. So here it's shown for example, for silicon, what's a typical substrate, and iridium, what might be a single layer on top for total external reflection. If we want to go to the total external reflection, one has to consider the critical angle. You can get a good estimate of this with the square root of 2 times this delta value. And if we plot the critical angle over the photon energy for those 2 materials, so for the silicon, you get a blue curve. Means at 8 kV, what's kappa K alpha radiation, a typical photon energy for the laboratory instruments, you are in the order of 0.2 degree. If you want to extend this, you can apply coating with a more high Z material. So we can lift this up to almost 0.6 degree. And that's here then shown for the reflectance versus the angle. That you can shift this to a certain extent, but not much more for the given photon energy. And if you want to operate at higher angles, then you need to go back to the crystals or to the multilayers, where you can get some break peaks at higher angles. So this means if we want to go to higher energy, it all gets a little bit more interesting, because we have to deal with smaller collection angles, and this typically means that somehow the efficiency drops, because if you have a smaller collection angle, then of course you are not able to collect as many photons. And as you see, we are operating here, at least for the multilayers, in the several degree range for those typical energies. So compared to optics for visible light, we really have to deal with very narrow angles. But that's of course also an advantage here, as we can do measurements with low divergence and then high angular resolution. So also regarding photon energy, particularly if we want to reflect the X-rays, one always has to consider the roughness versus the wavelengths. So, I mean, you all know this spectrum of the electromagnetic radiation, so radio waves, visible light, X-rays. And yeah, as said, if you want to reflect those, then the roughness needs to be somewhere in the order or better than the wavelengths. So if you want to build a radio telescope, it's quite easy. Yeah, I mean, those are really large-scale objects. You can walk on them. The roughness, I don't know it in detail, but I would estimate that it's somewhere in the centimeter range. But it still is able to reflect the radio waves, as they don't care because it's super smooth for them. If you go to the visible light, so if you have a metal surface, you need to do some polishing, but still can be done with this, what you can find in the shop, to get it reflecting. But if you want to reflect X-rays, the roughness really has to be in the sub-nanometer range. So the substrates that we typically have, you have 1 or 2 angstroms of roughness. So if you want to have substrates with this quality, you can use silicon wafers from semiconductor industry, because they are a mass-scale product. They are comparatively cheap. If you really want to have a 3D shaped surface polished by a substrate manufacturer, they have to really put some effort to get down to those roughnesses. And this kind of also makes it quite expensive in the end. So regarding the dimension of operation, I mean, you have 0D optics where just your light goes through like an absorber and so on. You can have 1D operation, null optics that are just focusing or collimating in 1D. And if you want to build an optical device for 2D operation out of this, you need to put 2 of them either in series, or you need to nest them. The advantage of this approach is the fabrication is typically easier. You get higher accuracies in terms of slope error and so on. The disadvantage is, particularly if you want to have something that finally operates in 2D, you have a more complex alignment, and also the efficiency drops. Yeah, I mean, that's just the square of the reflectance of the single device. And if your single device has a reflectance in the order of 80% or above, I mean, then the combined efficiency just drops down to 60% roughly, or 64. If you have some 1D operating device what only has 20% of reflectance, and you want to build a 2D operating device out of this, then it really drops down and might be a showstopper for some applications. One can also build 2D operating optics. So sometimes they're called single bounds, particularly for the reflective optics. Here the advantages and disadvantages are vice versa. So you just have one reflection, typically you get good efficiency, but the fabrication is typically more demanding. And yeah, in the end, we want to have an optics, we want to apply it somewhere. That's the schematics of the ID13 beamline at ESRF. So one beamline where we are typically testing our multilayer Laue lenses, what I will show you in the end of the talk. And in terms of X-ray optics, you do have the undulator. You will have some monochromator, probably some CRLs for pre-focusing, probably some mirror optics, some nano-focusing optics at the end. That's all on quite a long length scale. So from the undulator to the experimental setup, those are 97 meters there. What is required for this nano-focusing devices? And from the engineering point of view, it's kind of interesting that this all can be that stable. What was not shown in the schematics here, you have a lot of slits here. You have the power slits at the very beginning, some other slits to cut down the beam to get rid of scattering and so on. And one has to keep in mind that the thermal load of the radiation that comes out of the undulator, it's, as far as I know, in the order of 8-9 kilowatt. And I mean, in the end, what we get in our experiments, it's, I don't know, probably just a few microwatt or whatever. And all the rest needs to be absorbed here or dispersed, particularly by the power slits, by the silicon monochromator. And having something where you put almost 10 kilowatts on the devices, and still you get a beam here that's not drifting a lot, very stable, is kind of nice to see that this is all working. Why must the beamline be that long? Imagine you have a 100-meter object distance, so that's roughly those 100 meters. So the object that you want to image with your nano-focusing optics, that's the undulator source. Actually, I do not know the exact source size, but I guess those are in the order of a few single or a few 10 microns. So probably, let's assume 20 microns. You want to have a 1000 to 1 demagnification to get a 20 nanometer focus. This means you only can have a focal length of up to 100 millimeter. If you want to be on a geometrical limit, your optics might be better. If you need more space for the experiment, for example 200 millimeters, then you can only realize a 40 nanometer focus. On the other hand, we had an inquiry for another beamline, also quite long one, 90 meter, but in one direction we had a 300 micron source, and even if we applied our optics with the shorter focal lengths, from the geometrical point of view, the minimum focus size that we could achieve here, that's in the order of 70 nanometer then, though the diffraction limit of the optics is somewhere in the 20 nanometer range. That's also the reason why people are going for those kind of fourth generation synchrotrons. And if you want to build such a beamline, or you need to go somewhere in the storage room where you do have the small X-ray focus. So let's start with the absorbing optics. There are filters. I mean, probably you just want to attenuate your beam to limit the detector radiation, like a beam stop that's in the center of the beam, some X-ray shielding just for safety, or if you have a laboratory instrument, you want to measure with a high dynamic, so you can insert some filters if you have a high intensity beam, just to keep it within this range. You can have edge filters. For example, a nickel foil is good for copper radiation because it attenuates the copper K beta quite a lot, but the transmission for the K alpha is better. Of course, you're always losing photons with this. You may want to introduce windows, for example, for vacuum gas separation. So for the X-ray tubes, typically there are beryllium windows, and some time ago I looked into the purity of those beryllium window foils that are commercially available. And though for the ones that we had, the maximum weight content was in the order of 0.1%. If you just calculate the transmission, so on top here, that the dotted ones, that's ideal kapton and beryllium. But as soon as you introduce a bit of iron, this absorbs quite a lot. Yeah, I mean, it may drop down to something like 92% roughly at 8 kV. It means that you lose more photons than you must. Apertures, slits, pinholes. Usually the size and shape is of interest there. The scattering, so for our lenses we need apertures with the size of roughly in the order of 20 microns. I mean, sometimes we want to operate at 15, 20 kV and above, and then it's really a bit tricky to find some that small apertures that still attenuate in a good way. Of course, also the scattering from the apertures is of interest, so probably want to go to single crystalline material. And as I told you, for the ID13 beamlines or the power loading, also might be of interest, if you have this 8 kilowatt source and you still want to have just a couple of 100 microns opening, they also need to dissipate some power. Test patterns are also absorbing, not really optical elements, more test patterns. Those are well-defined objects like this Siemens star test pattern. They are used for the basic performance characterization of the optics of the instrument. So that's the kind of specimen that we use when we characterize our optics. That's just a transmission scan, a fly scan with a bit more pixels, so you can see that it's all not exactly flat because there were some vibrations or smaller drifts on the instrument. And they are available with, for example, 15 nanometer lines and spacers. If you want to go to 25 kV, you only have 3% of absorption, what is okay, but not much. And for me, at least at the few work that I do at the synchrotron radiation facility, so that's the most investigated specimen. If you develop optics, so then you typically do not have real samples, but you're looking at such items here. Refracting optical devices. So there are compound refractive lenses. So in general, I guess that's also not for you. You do have the complex index of refraction. You have this decrement value, what I was already talking about, and this is much smaller than 1, so almost 0. Since there's a minus sign here, so the real part of this is a bit smaller than 1. Means that you get total external reflection if you want to do a reflective optics, or if you want to do a refractive optics. In order to focus something, you need a concave lens shape in comparison to visible light, where you have the convex shape. And since it's very small, if you really want to have a certain focusing power, you need to put few of them in series. That you finally get some focusing. Common materials are beryllium, silicon, diamond, polymers, probably others. Focal lengths can be calculated with this formula. And as an example, so if we take silicon with a radius so that's the radius I'm talking about here, so the small radius of the curvature of 50 microns, you just have a single lens, then your focal length will be about 3.2 meters. So if you really want to focus to several millimeters, you need to put a lot of them in series. And in the end, you can produce those in 2D. so that you get the vertical and the horizontal focusing in once, but you are then somehow limited to the minimum radius of curvature that you can achieve, what's particularly of interest for the nano-focusing optics. Or if you want to go to the nano-focusing, then you may want to produce a set of 2 1D focusing optics, put them in series again, and then you may get something like a 80 nanometer focus or something like this. Those lenses here, they are often used as pre-focusing lenses for the beam lines, because as said, the entire beam line is something like probably 30 or 100 meter long. So even if you just have a bit more relaxed radii, you can achieve the focusing that you want. In terms of resolution for those kind of lenses, you are limited to the critical angle of total external reflection, because the numerical aperture for the classical approach cannot be larger. But this already means that without considering absorption, you may achieve something like a 50 nanometer focus. Of course, since those lenses are significantly long in beam direction, so probably several millimeters, you have to consider the attenuation as well, what then leads to a trade-off between the numerical aperture, the transmission, and then also affects the focus size. You can apply a few tricks like those diametrically focusing lenses, where the diameter of the outer diameter here shrinks if you come more close to the focus. And with this, at least something in the order of those 15 nanometers has been shown. There are new approaches here with 3D nanoprinting that instead of using a metalworking approach or those etching of the silicon, you can just 3D print those, also with very small radii of curvature. And that's the most recent development, at least to my knowledge, in this area. Face plates operate also in kind of zero or with refraction. So you may use them for aberration correction. So if you have a set of those CRLs and the focus is not as good as it can be, you can measure the wavefront with pyrography, calculate how a correction faceplate needs to look like, and if you then introduce this into the beamline from such a focusing scheme here, where you do have a main peak but a lot of side lobes, you can improve the focus quality a lot. And that's possible since a couple of years to do this approach. Now let's come to the reflecting X-ray optics. So there are 2 main types, capillary optics and then also the mirror optics. Let's start with the capillary optics. You can just use a single monocapillary. So that's quite a section of an ellipsoid of revolution. So you do have a focusing ellipse in 3D. So that's just a cross section here of it. You have a primary focal spot, a secondary focal spot. So all the rays that start here, hit the surface, are focused to the secondary focus. Typically, since we cannot really code a multilayer on this kind of capillaries, because the inner diameter is just in the order of a millimeter or so, at least for the hard X-rays, you have to live with the total external reflection. So you cannot make it much larger, because otherwise it will just not be reflected. They are typically made of glass that you can heat, then kind of squeeze it until it gets the desired shape. And glass is nice because typically the natural surface roughness is very smooth, so the smoothness that we need for the X-rays. But in the end, you do have a limited collection angle. It's still kind of broadband, so it reflects everything below a certain threshold of the energy. You can use those for micrometer focusing. You do need an internal beam stop and then also a pinhole to stop the direct beams hitting the focus or making some background. But that's all feasible applications. Micro X-ray fluorescence setups, and you can also use them as condenser optics for X-ray microscopy, as I will show later. One kind of special kind of optics. More common are capillary X-ray optics. So if you take a glass capillary with air or vacuum inside or helium, you can again employ the total external reflection. And X-rays that come in, and if they are below or hit the surface below the critical angle, they are reflected and make it all the way through the capillary. Then you take a bundle of this, have some nice technique to shape it, that it's small at the beginning, gets wider, gets tapered to the end. And you can use this to collect a lot of X-rays here and transfer them to a secondary focus. So the collection angle is much larger since you take advantage of a lot of capillaries. They are also broadband, low pass regarding the photon energy. So that's the transmission curve of such a typical polycapillary. That it's cut here, that's more because of the air absorption. Because below something like 8.6 kV, this just makes the difference. Also probably because of the window. But then towards the higher energies, it's kind of low pass. The focus size here depends on the photon energy, the channel size, and the secondary focal length, because you have a lot of individual capillaries. From every capillary, there is a kind of low divergence beam coming out. And they point all to the same focus in the best case, but it's not really by design focused to a certain spot. And this means if you want to have a 10 micron focus, you just have a couple of millimeters of secondary focal length or working distance that you can realize. Whereas for the monocapillaries, for example, you can have much longer distances. Applications mainly X-ray fluorescence, because that's kind of a spectroscopic method where I really want to take also advantage of the broadband behavior here. Now the mirror optics. For the crystal mirrors, they also work with Bragg reflection. So you may have silicon, germanium, lithium fluoride, graphite, or whatever. You get very narrow Bragg peaks because for the crystals you have a lot of lattice planes that contribute to the diffraction. So more than thousands. Therefore, the delta theta over theta is in the 10 to the minus 4 range. For the crystals, mostly you need to live with a constant period thickness. That means also that your Bragg angle doesn't change. Typical applications are flat mirrors, like those channel cut monochromators. What you can use to, for example, choose the copper K alpha radiation from a laboratory source, double crystal monochromators that are more used at the synchrotron radiation facilities. You may be able to use curved mirrors in a very narrow range. So there's this Johansen type monochromator, what you can use to focus the X-rays from a line focus X-ray tube to another line by fabricating a crystal that's bent in 2R and shaped in R, and then it If you do the geometry, yeah, it all leads to a focusing here to a secondary line focus. It's even possible to do a 2D focusing, even down to 10 micron. At least that's what the company specs claim for their system. But as you can see, this, or in order to do so, as far as I understood, this works best if you go to near normal incidence reflection, and if you calculate this for the typical crystals that are available, so means that you can only work with soft X-rays. But nevertheless, the source is here, it's reflected there and focused here to a narrow beam. But yeah, you are then limited to the angles that you have. And this also means that here you kind of only have a short working distance and probably the source or whatever is in the way. Mirrors that operate in increasing incidence of the X-rays, so you can fabricate them in 1D, in 2D. A flat mirror is just deflecting the X-rays for some reasons that you have. Probably for the monochromatization. You can use an elliptical geometry for point focusing from one focus to the other. You can use a parabolic shape for collimation, or if you have an incident, if you go the other way around, if you have an incident parallel radiation, you can also use this for focusing. If you want to go to the 2D optics, so you can also just rotate this geometry around the x-axis here. But typically this means that along the lengths you have very high radii of curvature in the order of several meters or several 10 meters. The small radius here, it's then more in the order of millimeters for the hard X-rays. And this means if you want to fabricate a single bounce optics, you have to make a very complex shaped surface, what makes it probably even impossible to manufacture this. And therefore it's sometimes limited to the 1D operating optics. If you look at those designs, so the angle of incidence changes at every point here along the length of the optics. I mean, those optics can be 40, 150, even 400 millimeter long. And to accommodate for this, you either can stay in the total external reflection regime, put a single layer on this to extend this edge a bit. You will get an achromatic behavior here up to the cutoff photon energy, or you can put an artificial crystal lattice on it, like a multilayer. I mean, here the minimum despacing that we can do is probably in the order of a nanometer. Typically more than 2. And this means that your optical wise also provides some monochromatization, what's good for lab sources. You get rid of the Brennstrahlung, even for the synchrotrons, to get rid of other orders or to narrow the beam a bit. In case of long focal lengths for the synchrotron, you can simplify the shape with a cylindrical, spherical, or toroidal surface, but that's just possible if you have certain focal lengths. Advantage of this is that we have long working distances. We are quite flexible with the geometry. We are not limited to a certain set of fixed deflection angles like for the crystals. Of course, we have to deal with aberrations, so we are operating in increasing incidence. The optics are long, so if we have a bit of waviness, this hurts. Also, since we typically want to employ the long focal lengths, if you do the calculation on the focus enlargement, we do have an optics with a focus to focus length here. I guess this was in the order of 400 millimeters. we have 2 arc seconds of slope error, we get a nice small focus. If we have 10 arc seconds, well, it's not much, but still it blows up the focus and kind of limits the effectivity of the optical system. If you look at the beam shape, there are 2 different grades of optics that we can manufacture. The beam, you might see some stripes that come or originate from the surface slope error. And what's also here, there's this elliptical focusing, but that's not a true imaging focusing, as we will see later on. It means you also have a limited field of view. As soon as you put the source out of the geometrical focus, the secondary focus will also be distorted. What's the reason why an optics that's calculated for 1 photon energy can typically not be used at another? There's this Kirkpatrick-Bates geometry, or KB. Is one way to achieve 2D focusing. So you do have individual mirrors for vertical focusing, for horizontal focusing. They are achromatic if you stay within the bandwidth of the optics, so as it still reflects. You have to live with a different magnification of both mirrors, because somewhere here is the source, somewhere there is the focus. And since there is a certain amount of space between the two, the first one is more magnifying than the second one, or demagnifying. So for example, what we built in the past this system is that we transferred a 20 micron source to a 140 times 160 micron focus at 3.5 meter from this system. And it's kind of complex because in order to align this, if you want to also steer the beam, you need a 6, 7, or in the full attempt, a 9-axis alignment, and what's then typically realized by a couple of stages. You can also use this approach for nano-focusing. So here an example from the ID16A beamline from Christian Morave at ISRF. So they achieved somewhere in the range of 10 to 20 something nanometer focusing. With their KB system, the working distance here was 25 millimeters from the exit of the mirror to the focus. Minus X means probably you want to put some apertures there to stop the beams that you do not want to have. One more recent approach with very ultra compact mirrors that was shown on the XRM conference last year from a Japanese group. They also reached something in the 20 nanometer range with very short mirrors, as you can see here, but then also the working distance is just in the order of a millimeter or so. And depending on what you want to put there, it might be okay, but it's, probably you want to have a little bit more. Montel optics, sometimes called side-by-side optics, nested KB optics, or we call it ASTICS. That's kind of a KB optics, but you put the two side by side. You have a little gap between the optics, and you have one half of the beam that first hits the one surface, then the other, and vice versa. This allows focusing to down to 10 microns, probably below. They are internally pre-aligned, compact. Means they are often used for the lab-based systems. You only need a 2 to 4 axis external alignment, like shown here at one of our X-ray sources. Here you have 4 alignment screws that you can switch to. 5 minutes. Okay, good. To the source. And they have their certain advantages. If you really want to do real imaging, there are those Volta type optics, 1, 2, 3, by combining 2 reflective mirrors. You get rid of the aberrations that the pure elliptical focusing has. At least to my knowledge, those are mainly used for the X-ray telescopes, for the soft X-rays, probably even to the hard X-rays. There is this Athena missions that was chosen by the European Space Agency, so they want to build a new X-ray telescope. And if you look at specs, yeah, that's quite amazing. I mean, that's just, you always have to live with those very tiny angles. So in order to get a larger numerical aperture, they put a lot of them in rings, in concentric rings along. And I don't know how they want to do it, but they want to have something like 1.4 square meter of aperture, almost 700 mirror modules, all kind of co-aligned, that they are all producing the same image. So yeah, quite fascinating if this works at some point. Okay, so let's come to the last point, to the diffracting optics. Fresnel zone plates are more common for imaging, for focusing. So you will have the zone plate law. What kind of gives you the idea how to construct your zones for the constructive interference. The resolution can be calculated from the numerical aperture, or it's typically related to the outermost zone width, what's in the same order. Focal length is proportional to the photon energy, means you have a chromatic lens compared to the other approaches. And in order to have an efficient lens, your zones need to have a certain extent in beam direction. So that's here calculated for air, for molybdenum and silicon. So that if you want to go to the 15, 25 kV range, so you need, in the best case, zones that are several microns or even more than 10 microns tall. And yeah, with the normal approach of the zone plates, at some points you are kind of either limited in the photon energy or in the diffraction efficiency. And yeah, since typically you do have air in between here, if you make them too small, they start to collapse. And that's a kind of nice study that was done at one of the free electron lasers, where after some shots, at least the outermost zones, they just collapse because they are not mechanically stable. And that's also one point where probably the Laue lenses do have their advantages. So I will skip this probably. You can do multilayer zone plates, what's kind of the same approach, but a different way of how to manufacture them. So you have a core, you coat zones on them, like for this kind of German cake, what's made in some regions. So the aspect ratio is not limited, but the accuracy and the limited aperture is kind of the challenging way. People tried this approach also with some decent results, but as you can see, the wire core here makes up a big part of the aperture, and then you just have a few zones at the outermost position. And good, so then let's see. Probably just a few words to the Laue lenses. I will also later on have a poster on this, so if you have some interest, we can also chat there. That's again going from the 2D approach to the 1D approach. So we just coat flat layers and cut lenses out of this. So it's interesting for high energies. Typically it works good above 8 kV, but even at 100 if you are interested. The resolution is also linked to the numerical aperture. The factor here is a bit different for the zone plates since we have a square aperture instead of a circular one. And also one good point is that we can employ dynamic diffraction because we have zones with, that are smaller than 20 nanometers. So we can go above the 20% diffraction efficiency of a classical diffractive lens. We do have several designs that are all with dedicated to longer working distances rather than going to the very narrowest focus that's possible. So if we look here at 12 kV, the working distance is in the order of 3 millimeters. So that already includes the apertures that are needed, or even much more for other designs, and still having sub 100 nanometer focusing going down to about 20. And yeah, this is how it looks at the ID13. Shorter focal lengths, smaller focus, and then the other designs. So you have some space to put your experiment in. Good. Then, depending on the timing, I can talk a little bit more, or we can stop the talk.
Just wrap it up a little bit.
Okay, then let's look. Yeah, that's made with magnetron sputter deposition. Few tricks. It's kind of challenging to code those. So the system is running for up to 10 days. You may need to code more than 10,000 layers for those designs. Later on, you cut your lenses, shape them with focused ion beam, and that's then your actual lens device that you can put somewhere. Focusing, yeah, quite simple. So you need the lens, you need some auto-sorting aperture to only have the first order focusing. There are several geometries. What I want to skip, probably also this. And if you want to have the 2D device, so you need to cross two of those 1D lenses. And if this is already internally aligned, so then you also only need 4 axes of, so you have 4 axes of the internal alignment, and then you need to have only a few axes for the external alignment to align them in the beamline, for example. So we did several attempts, like doing them directly on each other, one internal pre-aligned, now the new one, what has some benefits. And yeah, so we can get those 20 to 30 nanometer foci. That's just a transmission image of such a Siemens star with nice contrast, reconstructed beam shape. And probably the last point regarding the efficiency, the energy. We can cut out the lenses depending on the thickness for certain energies. So you may get a combined efficiency here for this design up to almost 30%. If you have an individual lens, you can use it not only at the design photon energy of 13 kV, but it still has a very broad energy range, but still it's achromatic. Yeah, you need some very monochromatic incident radiation, otherwise your focal length just shifts. And the other design with the longer working distance, here we do not have the issue that the dynamics of the period thickness along the aperture is that tall. So the overall efficiency after both devices can approach the 60% here, what is quite good for this value. So let's skip this. And applications, the group from Leoben, they are doing a lot of micromechanical experiments here where they can employ the larger working distances for their setups. I worked a lot on the full field approach, but we also tested with the MLLs. And then probably holography, typography, XRF mapping with high resolution, textual tomography as in this workshop, and probably have other ideas how you can employ those. And then finally that's the end of my talk, I would say. So that's just as a summary.